All right, thank you all for bearing with us here. So my name is Danielle Safer. I'm from the University of North Carolina at Chapel Hill, and it is my pleasure to be serving as the session chair for this session on immersive analytics and situated visualization. We're going to see all sorts of awesome stuff in virtual and augmented reality, and even bringing in some stuff from the physical world to really understand how we can explore data in different situated contexts. And we're going to start off with a bit of a bang here with an honorable mention for best paper, which is exploring interactions with printed data visualizations in augmented reality. This is by Wai Tong, Chu Chen Chen, Mongjia, Liu Yuho Lo, Lin Ping Yuan, Benjamin Bach, and Wah Ming Chu. So let's give them a round of applause. We have some nice certificates for you all after the talk. And with that, Wai Tong, the floor is yours.
So thank you everyone. Thank you for just for the introductions. Thank you for everyone to join this talk. So I'm going to present our latest papers today. So interactions is important in data visualization. It helps users to engage in data exploration. Generally, the interactions can be involved in two layers, so physical layers and the logical layer. So physical layer represents the interactions between the user and the instrument. Logical layer represents the interactions between the instruments and the visualization. For example, users can use a mouse to click on a zoom button and to zoom in the data visualization to get a detailed view for analysis. So to improve the efficiency of the interactions, direct manipulation is a very common and ways and become a mainstream in XCI and VIS domain too. So while most of the work achieves direct manipulations in the logical layer, like link and brush, however, a physical layer could also be designed for direct manipulation. So how? To achieve that, so researchers investigate the use of augmented reality. Augmented reality has brought us a new way to interact with virtual data in reality, as well as the ability to combine with physical objects for visualization and interaction. In particular, tangible objects like paper sheets, customized embodied axes, and globes can be used to interact with 3D scatter plots, three-dimensional data, and also spatial data. Following this line of work, we explore paper sheets as the tangible means to interact with visualization printed out of these paper sheets under AR. Because paper sheet is the most common physical medium for distributing data visualization. Moreover, paper provides a rich set of interaction affordance. We can use it as a touch surface, which can be moved and rotated in space. We can also fold it, bend it, or even tear the paper apart. We can also stack two papers to merge two bar charts into a grouped bar chart. With the help of augmented reality, we can better embed the physical parts with the logical parts, leading to a greater sense of directness. However, interacting with printed data visualization is still underexplored. Therefore, in this work, we are interested in explore how far can paper support direct manipulation for data visualization. Specifically, so we formulate our research question as what are the actions and commands that can be used, that can be supported by the papers. So to answer these questions, we first conduct an ideation workshop to collect possible interactions that maps the actions to commands. We invited 20 participants, mostly XCI and VIS PhD students, to read 10 printed data visualization and think about what they want to explore more from the printed visualization and how to achieve that. To accelerate the brainstorming process, we provide actions and command prompts from the existing literature. Based on the interaction we collected, we construct since there is a huge amount of interaction we collected, we construct a design space with 3 dimensions: commands, degree of information, and the number of paper sheets involved. The first directions, the commands describe how the visualization reacts to the paper actions. For example, the underlying data could be filtered or sorted, or the data visualization can be zoomed in and panned based on the paper actions. The second dimensions describe the type of information involved in the interaction, such as Boolean information and positional information. With more degree of information, users have more control to the visualization. The last dimension is the number of paper sheets involved. The dimensions describe the number of papers used in an interaction. By specifying the number of papers, we can determine whether the interaction targets on a single view or multiple views. Moreover, it can tell whether the interaction involves one hand or both hands. Based on the design space, we can describe the collected interaction in the four categories of interactions. First of all, Boolean interactions act as triggers to trigger some predefined commands, such as shaking the paper, and then we will reset the visualization. The second is the positional and area interactions. They act as on specific marks to activate some commands, such as filtering. So by rubbing on some marks, and it will filter that specific mark out. And the third one is direct plus value interactions. They act with directions to execute commands with directional information, such as I can rotate left or right to sort ascendingly or descendingly. Lastly, we have three expression interactions, which allowing users to act freely and perform some advanced commands. For example, we can highlight the mark with minimal values by overlapping customized paper sheet with the specific commands like calculating minimum value. So to evaluate the proposed interactions, we implemented a subset of interactions. We then conduct a user study with 12 participants to evaluate their user preference and also the practical viability. The results show that most of the proposed interactions were intuitive and engaging to use. Moreover, all participants are able to use the chosen interaction to perform the data exploration, which shows that they are very usable. So based on the results, we derived 6 design implications. The first one is to provide redundant actions to point actions. Point actions receive the most positive rating in all aspects. However, it is error-prone, so the pointing gestures are not recognized when there is occlusion. Since paper provides rich affordances, we can afford other actions with similar rating, like tilt to pen as shown in the figure. The second implication is to make use of different actions for command shortcuts. For example, when the data is biased or skewed, fold to zoom might be better than pins to zoom in some senses, because we can use in the one fold to zoom in instead of dragging around on the paper. The third point is to support selection and inverse selection to cover. That's because when the paper is getting large, it's harder to cover all the unwanted area for selection. The fourth implication is to utilize the semantic meaning of paper actions when designing interactions. For example, tilt to bend got a high score in both intuitive and engagement because it's similar to water falling off, just like the data point is now falling off from the plane. The fifth item is to balance the intuitiveness of the actions and readability of the text. For example, translate to zoom is intuitive as shown because it's matched the physics that close objects becomes larger and far objects get smaller. However, the text is getting hard to read when it's too far away. One solution is to fix the text at a certain distance for reading and allowing the visual patterns to follow the actions, movement, and for intuitiveness and engagement. So to conclude, we have shown a huge design space for combining papers and interactions to support data interactive data visualization for data exploration. And in the user study, we saw the expressiveness that everyone can use the paper actions to do the data exploration. And in the future, we think that beyond papers, we can combine with data visualization to provide more interactive visualization to different medium. That's all for the presentation. So if you have any questions, feel free to ask. Yeah.
And again, a reminder, please post your questions on Slido. So we actually have our first question here. So one thing that's always tricky with this kind of research, right, is getting those 3D demos into the 2D visuals. And in some of the visuals, it looks like there was a little offset between what we saw in the paper and what we saw in the immersive headset. So do you know how that artifact might have manifested? Is that intentional? Is that just viewpoint? Where might that be coming from?
That's a good question. So in the video, so there's some offsets between the virtual contents and the paper. So that's because while the recording, so we are using the camera from the HoloLens 2. So it will be there's offsets different from our eyes. So in the user study, so the virtual objects is perfectly aligned with the papers. So when you are from the perspective of human eyes, so that's because of the recording issue. Yeah.
Awesome, thank you. So another question here from Matt Brummer, which is how much of this design space could be applied to mobile AR if we take this off the headset? Is it really specific to HMDs, or can this be generalized to other applications?
Yes, that's also an interesting question. So I think we can generalize the interaction to mobile AR for the mobile data visualization. But one thing is that since if we generalize to mobile data visualization, so we are limited to some interaction. So because we need to use one hand to hold the phones and one hand to interact with the paper. So the interaction might be limited because we are holding a phone. So for example, like folding is a bit hard to do when we are holding a phone. So that might be one limitation if we want to use this design base to the mobile data visualization.
Awesome. And one last quick question here. So, when we're dealing with paper, we're dealing with 2D. When we're dealing with more immersive augmented reality, we're often dealing with 3D. And I know there's been some work in the community in the past with more hybrid approaches, kind of like Mélanger, where we're doing space folding for interaction. One of the questions that we're getting online is, how do you see this work extending back towards the 3D space?
Yeah, that's a very good question. So what you are asking is that because so in paper, so there's 2D and we are interacting with a 2D space. So how can we bring back to the 3D? So I think in the recent research, so there are different researchers are researching like extending from the 2D visualization to 3D visualization. I think we can use some hand gesture to pull the visualization out from the papers to get it back to the 3D. And also, so from the medium side, so there's one way. So another way is that we can consider 3D printed objects, so such that we make the medium space or the physical space also in 3D. So that's how we can also bring the 2D visualization to 3D visualization.
Fantastic, thank you. Let's thank Wai Tong one more time.
Yeah, thank you. Thank you very much.
So our next speaker will be presenting RagRug, a toolkit for situated analytics. And this is work by Philip Fleck, Amy Souza Calypso, Sebastian Hubenschmidt, Michael Settelmeyer, and Dieter Schmalstig.
One second. Here we go. Perfect. Hello, everyone. Thank you for the nice introduction. So today I'm going to talk about our toolkit, RegRug, and it is available on GitHub. So since I cannot cover every detail here, take a look at the paper and also on GitHub where we have even more videos and helping material. This was a joint collaboration between the guys from Stuttgart University, Amy Sousa Calypso and Michael Sedelmeier, Sebastian Hubenschmidt from the University of Constance, and Dieter Schmalstick and myself from the Technical University of Graz. So we're going to talk today about situated analytics, and I will take you with this journey. So we are looking at such scenarios where you have some situatedness. This means that we have some sensors around. They might give some real-time data, and then we have some labels pointing to the direction where they are, and we get some real-time visualizations. And there's also some historical data on the right-hand side. But there's more to it that I will come at the end of the talk. Let's play situated analytics. So I guess many of you are very familiar with immersive analytics. So where you have an immersion of the visualization, but it has no place in the world. Going to situated analytics, you have some referent with a certain meaning to it. This might be like a device, like this microphone, or something different, or even something passive like the paper sheet that we saw in the previous presentation. So this brings us into the area of the situatedness. In the traditional pipeline, the user remains in the physical world, and he only interacts with a 2D or pure virtual world like a display on a screen. So if you take this pipeline into the situatedness, then suddenly we get a perceptually situated display like a HoloLens, for example, and we get reference. But to represent all this reference, we also need something like a physical virtual world model. This is also referred to digital twinning or similar words. So the reference that we will talk about may be active, like sensors, or passive, as I mentioned before. The physical virtual model is actually the key to establish the semantic connection between an object like this device here and the representation of it in its virtual world. So it has been mentioned a long time ago, like in mirror worlds or digital twin, and it's even an industry keyword like big data. How much sensors do we have? How much data is coming in? So the whole setup leads to a number of research questions. Let me get quickly through them. First of all, we have to decide, how do we deliver visualizations in augmented reality? Or how do we create a visual encoding for augmented reality? Furthermore, how do we make visualizations react to the context, so make them context aware? Also, for importance is, how do we create a comprehensive physical virtual model that is adaptive to the environment that we want to make immersive? And furthermore, how do we make visualizations react to the changes in the world? For example, we move something around. So with RegRug, we try to answer a lot of them to a certain degree, and I will quickly guide you through the process. So to answer the first question, obviously, we use something like a device, like a HoloLens or similar. On top of that, we can establish unity with a broad reach, and we use toolkits like the mixed reality toolkit to bring this further. Secondly, how do we create a visual encoding? So we can use tools like the IEEE, the Immersive Analytics Toolkit from Cordail, which utilizes geometric shaders for speedups. And we can now have a Unity application with some visualization. Now, if we have that part, we have to step into the world of IoT. This might not be very familiar to all of you, but there are a lot of tools used amongst industries. For example, Node-RED that is used to do orchestration of sensors. So the special thing about this is it uses visual programming to establish some sort of data flow which can represent an application. Additionally to that, we can add some databases. We have messaging, in this case, the MQTT transmission protocol. And with that, we got a powerful suite to deliver the data. So in detail, we had to extend the IATK to support reactive programming. And furthermore, we had to extend IATK to be aware of real-time data. Additionally, we can write data flows in Node-RED. Visualizing the left-hand side, which is our IoT hub, and the right-hand side, which is an application running on the Microsoft HoloLens, we still would have to write application code inside the application. And now if you take these two different environments, every environment would have to hold its own code. So this becomes a little bit cumbersome. What we find out was that we can run a JavaScript interpreter inside the HoloLens and apply the same data flows that we implement in Node-RED on the device. And therefore, we can implement a uniform programming language which follows the functional reactive programming, also known as a data flow. So to resolve the image from the beginning, what we see here is a complete environment that is accessible and explorable with a HoloLens, which also implements proxemics. And to resolve this, we see the charts here in green with the red arrows are implemented using a data flow. The position of the devices in the environment is implemented with a physical virtual world model, which is here referenced in orange and called device. To get some HTML or similar information into it, we can use plain JavaScript if we decide to, and generate these labels with its leader lines. And additionally, we can use tools like Grafana to represent historic data. So this concludes my talk. Thank you for your attention, and feel free to ask any questions. Thank you.
Great. Thank you so much. So our first question on Slido comes from Michael Becker. How many messages per second from the IoT devices can RAGRAG handle? Is it usable for critical infrastructure sensors with 100 hertz or more?
So that's an interesting question because we use open source software for our backend. So this means the databases can scale horizontally and vertically, and also the messaging, and we can apply load balancing to it. For example, our database InfluxDB can handle 1 million inputs per second. So this should be plenty for most usable scenarios.
Fantastic. So one question I was curious about, looking at a lot of the architectural diagrams that are coming up on here, it seems like, especially if you go back earlier and you talked to that research question slide, you're crossing a lot of subfields in computer science in really interesting ways. And I know as Viz folks, we're so used to being in service of the discipline, but this strikes me as also a situation where other subfields of computer science may actually serve in service to Viz. So I'm curious if you can talk briefly about, kind of based on the work that you've been doing, what do you see as the most important next challenges for our community? And where do we need to turn to others for innovation to really drive this agenda forward?
That's a very good question. So you can imagine publishing this work was a little bit of effort because it takes like part of different disciplines. And the takeaway message is that you can have a computer science backend like this and use an application, and then you can cherry pick the parts that you want. So what I discovered from my augmented reality background is that a lot of works use like this default data sets, like a stock exchange or something similar, or cars in the US. And this was the turnaround point to go to real-time data that is inside produced. So this might be a takeaway message.
Fantastic. One other thing on kind of the hardware side is I know you mentioned the HoloLens, and
Yes.
you know from some past experience, I know that the HoloLens sometimes has unique development constraints compared to many other headsets or other VR/AR platforms. How robust is RagRug to moving across platforms and across devices?
So we provide in client a raw project for that and also builds, and we have successfully tested it on iOS, Android, HoloLens 1, HoloLens 2, desktop PC, and there's some Linux version working somehow. But there are like checkboxes, not every device supports everything, so you have to find out. Thank you.
Fantastic. And one last question for you here. I might have missed this in your talk, but where can we get access to this to play with it a little bit?
It's on GitHub.
Perfect.
So you can find it here. Just search my name likely. And there are also tutorials. A tutorial is held at ISMA right now. So this might also be recording, and it's also used in a class in the University of Bonn for teaching. So there's also a more than 1 hour recording of a tutorial. And I provide also virtual machines so that you have an easy time setting it up, because you can imagine it's a little bit of
Fantastic. Thank you for making that so easy to dive into. And let's thank our author one more time.
Thank you.
So our next presentation will be a virtual talk. This is on Puzzle Fixer, a visual reassembly system for immersive fragments restoration. And the authors here are Shenin Ye, Zichuan Chen, Zhongtong Chu, Kang Li, Juntong Liu, Yi Li, Guoha Geng, and Yingkai Wu.
Today, I will talk about Puzzle Fixer, a visual reassembly system for immersive fragments restoration. Reassembly is a common task that reconstructs the fragments of a fractured object to restore its initial state, which is imperative to recover the function and value of the broken objects, such as reassembling picture puzzles and cultural artifacts, and reconstructing physical evidence in forensics. Thanks to the advances in geometry processing, automatic reassembly approaches have been developed to reduce human efforts. These methods identify fractured regions, search for adjacent fragments, and gradually assemble the entirety. However, their success rates are still far from satisfying. Caused by weathering and erosion, fragment surfaces are easily damaged, which causes large noises and ambiguities. These fragments can cause illness reassembly results. Thus, experts need to fix errors manually. Traditionally, reassembly errors are fixed with direct interactions, which requires searching for reassembly alternatives manually. Another strategy is to explore a pre-computed candidates. However, numerous candidates limit match searching. Due to the 3D nature of object reassembly tasks, various work adopt VR techniques that enable realistic perception and intuitive fragment control. However, correcting reassembly in VR faces two challenges. First, finding the best correction solution is laborious. The massive candidates are overwhelming for experts, as they need to determine their correctness based on observation and comparison of shapes and match relations. Second, it is challenging to correct alignments between multiple fragments. Direct mid-air interactions suffers imprecise problems when aligning various faces. Moreover, transforming fragments while checking their correctness from overview to details increases difficulties. Hence, we aim to develop an immersive reassembly system for restorers to detect errors, find correct matches, and refine detailed alignments. We propose Puzzle Fixer. It augments objects with 3D node link network for error match reinspection, generates candidates and clusters for reassembly exploration, and provides instant visual and force feedback for fragment alignment. To detect errors, we first describe the reassembly results with 3D shape and match relations. Shape data contains fragment models, which depict what the reassembly looks like. The relation data is a matching graph that includes fragment relations and matching scores. explaining the fragment relationship and their match quality. Based on the nature of reassembly correction, we further describe these types into 3 levels. Candidate level data refers to a set of objects with different alignments, which provides an overview of all solutions. Fragments level data focus on one object and provides match evidence such as a surface texture and fragment match score. Face level data comprise faces and their relations on each fragment. Based on the data, we collaborate with domain experts and develop a 3-stage workflow, including the inspection, exploration, and confirmation stages. In the beginning, experts identify mismatches from the reassembled object, disconnect the error relations, and divide the object into multiple parts. To visualize the reassembly results, we embed the matching graph with 3D models using a skeleton metaphor. The edge is presented by a 3D tube, where broken edges indicates missing matches. Scores are encoded by the color of faces and edges. Gesture to modify the graph intuitively. The touched edges will be disconnected, and the object will be divided into several groups. Next, user can select a group to see how the remaining fragments match with it. In the exploration stage, experts explore candidates to find the coarse matching strategy and then determine the correct matching fragments. To solve the challenge caused by overwhelming candidates, we distribute them based on their skeleton similarity. PuzzleFixer first calculates chamfer distance between skeletons, then perform t-SNE to obtain candidate distribution on the 2D canvas. We further cluster candidates based on their center locations using DBScan, and then design visual summaries to reveal matching patterns. PuzzleFixer then generates a visual summary of each cluster to avoid visual overwhelming and provide levels of detailed searching. We average the skeletons to present the matching patterns of the cluster and avoid showing the surface because it contains detailed information that requires much time for in-depth analysis. Such visualization fulfills our design considerations and has many benefits, such as expressive that shows the match patterns. It's representative since it presents the thumbnails of the cluster. It is also succinct as it does not contain details for judgment. With selected candidates, experts need to check their faces, refine their alignments, and enter the next reassembly iteration in the confirmation stage. Given the difficulties, such as checking the facing faces while aligning, this stage aims to enhance relation awareness to guide manual alignments. PuzzleFixer provides visual feedback that instantly shows the aligning matches with a 3D dotted tube. When alignment is complete, the system automatically uses a magnet metaphor to assemble the fragments. PuzzleFixer also provides force feedback to avoid damaging the aligned faces. Transformations that lengthen the confirmed edges will be scaled down. Thus, the user needs a larger moving scale to move away the previous aligned faces, which prevents damaging previous alignments while aligning new faces. Finally, based on the refined alignments, PuzzleFixer calls automatic methods to reassemble the left mismatches not included in the chosen candidate and starts the next iteration. Here is an example of refining the reassemble style. By observing the skeleton, the user noticed the errors from the top right area. The gaps here reveal that these fragments are poorly aligned. Thus, he disconnects them and selects the largest group to enter the next stage. The system shows there are 3 categories. The user first observes their match patterns and their coarse matching shape to find an interesting one to correct its alignment. When he gets closer, a reassembly in miniature is appeared to show the overall appearance. He first aligned a face pair according to visual feedback. Then he rotates the fragments to align another face. The force feedback limits the fragment's transformation that would break the previous match. When he releases the grab, the fragment automatically aligns according to the visual cues. Similarly, the user aligns the next fragment. This time, he finds that the right half of the object is not matched well. Thus, he disconnects the corresponding matches and looks at possible solutions. Through comparison, he selects a solution and manually aligns its face with the help of instant feedback. Finally, the system adjusts all the fragment transformations and completes the reassembly. We invited 6 domain experts to evaluate PuzzleFixer on a real-world culture artifacts dataset called Marlin Broken Steel. The experts were asked to reassemble their units fragments by using our system. All participants successfully corrected the reassembly within 20 minutes. The post-study interview confirmed the usefulness and usability of our designs and system. Besides, the participants also suggest insightful recommendations for further research direction. In summary, we present a virtual reassembly system, PuzzleFixer, to help experts refine the defective reassembled objects. Our system presents embedded networks to augment mismatch inspection, generates visual summaries for levels of detail exploration, and provides instant feedback for efficient alignment. That concludes my presentation. I'm ready to take questions. Thank you. Hi, I'm
Great. Thank you so much. It's kind of fun to see that. I'm getting flashbacks to a lot of old like mystery thrillers and things like that where we're seeing all the artifacts come together. We've got a lot of questions here on Slido for you. The first being, what does VR provide for your tool that you would lose in an interactive desktop?
Thank you for the question. First, the interaction for the users is naturally 3D, that the user can use 6 degrees of freedom to control and transform the fragments, and which I think the desktop is hardly to provide such features. And then the perception for the fragments is also 3D, so the VR provides a better perception for the users to control or observe the correctness for the matches.
Great, thank you. And I think the next two questions on Slido here are fairly related, which is, what does the pipeline look like, right? What you presented here is largely in the virtual space, but in theory, this is to create and support action in the physical space. So once the fragments are fixed in VR, how are the fragments connected to real life to actually fix or reassemble the artifact? And similarly, would you see some trade-offs between doing this in VR versus moving this, for example, to AR to do the same kind of assembly task with the real pieces?
Thanks for the interesting question. The pipeline here is to first we have a reassembled object, but it's have some matches error matches, and so the users use a 3-step frame workflow that inspect the errors and search for the correct candidates, and then to manually line the details. So if we move or transform the VR to the AR, firstly, if the user transform the physical fragments, there may be some limitations. For example, maybe the fragments is too heavy, or the fragments is maybe suffer from some second maybe suffer from broken how to say that the physical fragments may be fatigue, so there are many problems for the users to use the AR and help the field workers to reassemble the physical fragments.
Awesome. Thank you so much. Let's thank our speaker again. So our next talk is also a virtual presentation. It is effect of view layout on situated analytics for multiple representations in immersive visualization. And this is work by Zhenwen, Wai Sheng, Lo Shan Wang, Yihan Liu, Mangliang Zhu, and Wei Chen.
I'm Zhen from Zhejiang University. Today I'm pleased to introduce our paper, Effects of View Layout on Situated Analytics for Multiple Representations in Immersive Visualization. This is joint work between Zhejiang University, Hong Kong UST Guangzhou, and Zhengzhou University. Let's start with background. Recent advancements in interaction and immersive display technologies for augmented reality have increased the popularity of situated analytics in a variety of applications. Multiple view representations have been demonstrated to be effective for data exploration in immersive visualization. However, due to the nature of the third dimension, there are challenges for using multiple view representations in situated analytics. In 3D space, view occlusion happens, and the angle of view causes perspective distortion. In addition, representations positioned at different depths appear in different view sizes. These challenges hinder cross-view data analysis, such as comparing values in different views. Traditional 2D desktop interfaces leverage visual linkage and coordinated interactions to mitigate the issues. However, directly adapting these techniques to immersive visualization may bring in other issues. For example, visual linkage rendered in immersive displays with a relatively small field of view can easily cause visual clutter. Our work tackles the challenges from another perspective. We focus on view layout that concerns the placement of multiple view representations in 3D immersive space. Three categories of layout design in immersive visualization have been summarized. Embedded and linked layouts are simple to implement and have been commonly adopted in situated analytics, but both have limitations. In comparison, the mixed layout is a lack of exploration. To design an effective layout, we summarize design considerations for achieving high situatedness and effective analytics simultaneously. We consider the situated analytics scenario as a composition of the user, reference, and views. When placing views, we need to consider three types of relations between views, reference, and the user. If we only consider the view-to-reference relation and put them in close proximity, then we get the embedded layout, which only provides high situatedness. Alternatively, if we only consider the view-to-user and view-to-reference relations, then we get the linked layout, which promotes efficient analytics. So, the problem is how to design proper proximities between views, reference, and the user to balance situatedness and analytics. Moreover, we perform an in-depth analysis on design trade-offs between situatedness and analytics. Here, we list the requirements we distilled for designing an effective mixed layout. To fulfill the requirements, we propose a force-directed approach to automatically position multiple view representations using a cylindrical reference frame. The cylindrical paradigm has been widely adopted in immersive visualization to represent positions in 3D space. Specifically, we put the user at the center and model all other positions in 3D space as positions on cylindrical surfaces surrounding the center. For simplicity, we keep a 2D plane that tangent to cylindrical surface to render views, rather than bend views to fit the cylindrical layout. Then, we design a twofold force-directed method that employs forces to balance proximities between the user, reference, and views. First, we choose to place all views on a common cylindrical surface. All views receive attractive forces from the user and the reference. In this way, the radius of view position is determined by the view-to-user and view-to-reference relations. Second, we perform force-directed layout on cylindrical surface to translate view positions. By attractive and repulsive forces between views and reference, our method removes occlusion and balances view-to-view and view-to-reference proximities. This video shows the effects of our layout design. To facilitate data exploration and layout configuration, we design view arrangement interactions for fine-tuning view layouts generated by the automatic approach. User can move a view on the cylindrical surface with one hand and pull the surface closer or push it farther with two hands. We also provide an automatic view alignment function for view arrangement. All selected views will be restricted on a common cylindrical surface and placed side by side. To validate the effectiveness of our approach, we conducted a formal user study that compared the layout created by our method with embedded and linked layouts. Experiment results show that participants accomplished filtering and connecting centered tasks significantly faster with our layout, and the advantage is more significant in complex things. User feedback also validates our prototype system in terms of usability, utility, workload, confidence, and satisfaction. The study reveals some interesting findings. Situated analytics is often regarded as a holistic feature and benefits for immersive visualization. However, our study shows that the design recommendations for improving situatedness and those for facilitating analytics with multiple view representations can be hard to accomplish simultaneously. The finding opens up research opportunities for better understanding the relationship between situatedness and analytics in immersive visualization. Our work has presented an effective method for balancing situatedness and analytics. There are several promising directions for future work. First, we plan to improve the interactions of our prototype system from the perspectives of modality and accuracy. Second, we would to improve the generalizability of our layout adaptation method. In conclusion, we have presented an in-depth study on the effects of view layouts on situated analytics for multiple view representations. This work illustrates a promising area for future research on situated analytics. More conceptual and empirical research is needed to achieve a better understanding of design space dimensions for situated analytics. That's all. Thank you. Hi, I'm Zhen from.
Great, thank you so much. So, a reminder to post any questions you have for our speakers on Slido. I want to kick things off here with a question about essentially attentional focus and peripheral vision, right? When we're looking at these kinds of graphs, essentially arrayed egocentrically around the viewer can only actually really focus on one or two graphs at a time for the most part. So I'm curious how this particular method might change the kinds of comparisons or the ability to precisely compare data that people are able to accomplish with multiple graphs based on this forcing data and forcing information more into the periphery.
Sorry, can you repeat the question?
Yeah, for sure, for sure. Let me try and state this in a little simpler way. My apologies. I'm curious, basically, if you are kind of arraying all of your graphs side by side, where my impression is in other layouts, you can kind of overlay them or have them both, in methods where you're kind of taking advantage of multiple dimensions. So I can have 2 or 3 or 4 graphs that are arrayed vertically, and then you have them horizontally as well. It seems like, if I'm understanding your method correctly, it's privileging kind of this horizontal projection along the cylindrical surface. So I'm curious, what are the trade-offs, in essence, of kind of changing and moving the views out in the visual space?
So,
We can always take it offline too. So let me go ahead and ask a little bit different question when it comes to the kind of displays that you're presenting here, right? One nice thing about this is that it is kind of doing that automatic layout and dealing with some of the occlusion issues we often see when we're dealing with situated analytics. But I'm curious, how scalable is the approach? How many graphs are you all able to usually comfortably fit into your display using this approach?
we use 3 views and 6 views in our studies because we found the field of view of our devices, that is HoloLens 2, has limitations. So put too many views in the field of view is not realistic. So we only test 3 views and 6 views. But in theory, our method should support more numbers of views. But due to the limitation of the field of view, when we introduce more views in the application, we may take more considered to we may consider more about how to design the views to fit them in the limited field of view.
Great, thank you so much. We have a quick question here from Melanie Torrey. Do you think the chart type would influence how different charts would perform in these 3 different conditions?
Yes. That's a good question. We only test the bar chart in our user study because we think that it has it's a commonly used chart type. And for more different chart type, users may take different actions when comparing them or get some insights from them. So maybe future work could explore how to fit the layout, how to adjust the layouts by the type of chart.
Great, thank you. So let's thank our speaker again. So our next topic is RoboHapAlytics, a robot-assisted haptic controller for immersive analytics. And the authors on this paper are Xiaozhang Dai, Tim Dwyer, Barrett Enns, Jim Smiley, and Lonnie Bensenson.
Hello everyone. University in Melbourne, Australia. Hello everyone, my name is Xiaozhang Dai. I'm a PhD candidate at Monash University in Melbourne, Australia, and I will be presenting our work on RoboHapAlytics, a robot-assisted haptic controller for immersive analytics. Immersive environments like virtual reality has shown its great potential to present and explore data, especially three-dimensional data. and how to interact with the data is always an interesting topic. Currently, the most common way is using the VR controller with recasting or hand tracking with mid-air interaction. However, both of them can only provide very limited guidance. One way to increase the guidance is tangible feedback. Many work has explored that using tangible feedback can leverage natural human interaction with everyday 3D objects to facilitate interacting with digital content, like using a parallel sliders on each orthogonal axis for a volumetric range selector, and the tangible feedback in this case allow a more precise interaction. Where some other researchers are interested in generating simulated haptic feedback for interactions. By changing the actuator setting, the same device can be used for different situations. Like a motorized slider can switch its behavior between a normal slider and a step slider. A more natural and realistic way for interaction would be encounter-type haptics, where a supporting device like a robotic arm changes the position of the physical controls in order to meet different interaction requirements. With an accurate and fast tracking system, an encounter-type haptic device can theoretically allow any interaction within a given space. However, not many approaches of the encountered haptics were used for data analytics, and most of the approaches are designed for static interactions. Hence, we built a physical slider and mounted on the end of a robotic arm as the encountered haptic device for dynamic interactions. Here is one of the potential use cases of our device. We use a set of Vicon camera for the accurate position tracking and the glove for the hand pose tracking. Since we're using a robotic arm to extend the slider's range, we also built a long physical slider as the baseline to compare the difference. When the slider lobe is moving to the end and enters a predefined buffer region, the robotic arm is actuated to move in the same direction, and the speed is positively proportional to the speed of the knob. Meanwhile, the DC motor on the slider generates a proper amount of force feedback based on the speed of the robotic arm to ensure the resistant force on the knob is similar to a real long slider. Here are some short demos of the features: the encountered haptics, a force feedback, and the speed adaptation. We have conducted a control experiment to evaluate the performance difference between three conditions in order to control the slider in VR. The conditions are interacting with a long physical slider, interacting with a virtual slider only, and interacting with our encountered haptic slider, also referred as dynamic slider. Ideally, the dynamic slider can perform similarly to the long physical slider, and better than the virtual slider, where interaction with mid-air gesture is one of the most common methods. All three conditions have the same VR view during the experiment, and the experiment is designed to ask participants to move the slider knob to a random generated point and measure the time cost and accuracy. The position of the random point is restricted to three ranges based on the position of the slider knob. As you can see, for the average time cost, the physical slider requires least time to complete the task for all three range conditions, and the dynamic slider is slightly slower than the physical slider. Virtual slider in general takes the longest time to finish all the tasks. From the average error result, there is no obvious difference between the dynamic slider and physical slider, but both of them are significantly better than the virtual slider in terms of accuracy. From the Likert chart in our post-study survey, we can see that most of the participants prefer the physical slider as it is the easiest to use and can generate the most accurate result. Our dynamic slider is the second preferred choice, and the virtual slider is the least preferred one. We have also developed 3 potential use cases of our dynamic slider. The first use case is a straightforward application of the dynamic slider with extended range but fixed orientation for a time series line chart. The second use case is an example of using one dynamic slider to represent multiple virtual sliders of different orientation in VR. In this example, user can use a virtual slider to control the cutting plane of a 3D skeleton. For each orthogonal axis, there are 2 sliders. Therefore, one physical slider is used to represent all 6 virtual sliders in VR. Our last use case is a virtual reality adaptation of the dim-based scenario. Dim-based is a manipulation technique for interacting directly on the virtual items in visualizations to enable exploration of the time dimension. By selecting the virtual item, a trajectory indicates the change of that item over time, and moving along the trajectory updates the whole visualization to reflect the new time. We implemented the dim-based technique on a scatter plot in VR. By selecting one data point, the temporal changes of that point is highlighted, and the user can move the data point to a previous or next time slot to update the whole scatter plot. There are some aspects can be improved to optimize the performance of our device, and also some future work to do to increase the versatility. First of all, our device relies on a marker-based infrared motion capture system, which is currently the most accurate and fastest system for real-time hand tracking. Although we have tried several types of camera-based hand tracking devices, the accuracy does not meet our expectation. If a better tracking system that allows bare-hand interaction can be implemented, users would have a better immersive experience. Also, our robot speed is strictly limited to a very safe level to avoid any potential accident. As a result, it directly restricts the maximum speed allowed during the interaction and increases the delay before the user can actually touch the physical controls. Additionally, in our current stage, only one slider and a rotor encoder in one of the use cases are involved. There are many other physical controls and actuators can be attached as well. With more controls available, we can provide a general solution to fit all the required interactions for data analytics in VR. In conclusion, we have built an encountered haptic device with a slider control for dynamic interactions. We have designed and conducted a controlled user study to evaluate the performance of the dynamic slider system and compared it with 2 other interaction conditions. We have also implemented 3 use cases to demonstrate the usability and the applicability of our dynamic system. We hope this work can inspire others to create a more versatile solution for immersive analytics. Thank you for watching.
Great, thank you so much. So our first question from Slido is very pragmatic. It's wondering essentially about the cost. How difficult is it to set up a system like this?
Well, thank you for the question. I'm not really sure the cost. Well, I can say the robot is quite expensive.
I think that's probably a fair estimate there. So our second question is looking more at kind of the trade-offs of the techniques that you're using. So what is the advantage of using the mechanical slider mounted to the robot compared to just using the arm itself to simulate the movements of a slider?
Well, thank you for the question. That's a really good one. In the ideal world, of course, we can just use the robot to simulate the slider behavior. But the fact is there will always be some delay during the interaction and when we can activate the robot to simulate the behavior. By using a mechanical slider mounted on the robot, first of all, it will be much easier to implement. And the biggest advantage is if we have a slider on the robot, if, for example, the user need to have a really precise selection, In that case, the robot does not need to move at all. So in that case, the slider can be our dynamic slider will behave exactly the same as the long physical slider. So in that case, the haptic feedback will be the most realistic.
And one last quick question here, I think it's reflected in a couple of the questions. How might you think about the portability of this technique, right? You showed a tabletop robotic arm. Are there other directions that you might think about extending this that might make it more portable as the user moves about in space?
Yeah, that's another good question. Thank you. So in the future, if we're actually planning to think about in that direction, like we can put some wheels or maybe some other ways to make the robot follow around you. So the robot will not just stand on the table itself. So in general, we can increase the available interaction space, way bigger.
Great. Thank you so much. Let's thank the speaker again.
Thank you.
And the last paper of this session is Labeling Out-of-View Objects in Immersive Analytics to Support Situated Visual Searching. And this is work by Tika Lin, Yalong Yang, Johanna Bayer, and Hans-Peter Pfister.
Hi, can you all hear me? Yeah. Hi, everyone. My name is Tika Lin. I'm a PhD student at Harvard University. I'm super excited to be here because this is my very first VIS presentation. So in this paper, we present an empirical study on AR label design for out-of-view objects to support situated visual searching. So the motivation for this study is based on the frequent user needs to perform situated analytics in the real world. We often compare data and search for targets of interest, such as looking for a product in a supermarket, comparing menus of the surrounding restaurants, or identify players in a live sports game. While this information is available digitally, how to search and compare them effectively is a visualization design challenge. Broadly speaking, labeling techniques are used to annotate targets of interest on a given view. In a 2D visualization, the main challenge is to address dense target in a small view. So external labeling, zooming, or filtering techniques were studied. On the other hand, in the AR scenario, the real-world objects are usually sparse in the physical environment, and the physical targets cannot be manipulated or scaled like the digital targets on the 2D screen. Therefore, directly annotating the objects in the field of view seem to be the most popular method, such as embedding or external labeling. However, since real-world objects are sparse in a large space, users have to physically scan the entire environment, which can be inefficient and physically demanding. Therefore, we found there is a current gap in labeling targets that are outside the field of view to support situated visual searching. In our study, we want to understand how to place labels in AR to effectively support visual searching tasks. We first systematically explored the design space of AR labels with a focus on out-of-view objects. We then design and evaluate 5 distinct labels in a control user study. So to identify the design requirements for AR labels, we first conduct a goal and task analysis. 2 goals were identified. First, the labels need to support spatial searching by visualizing the spatial relationship between the targets and the user. Second, labels need to support situated visual analysis tasks by providing extra information. We then identify 3 fundamental situated visual searching tasks based on the typology of abstract visualization tasks by Bremer and Monsner, including identify a single target, compare multiple targets, and summarize data across targets. Following identified goals and tasks, we systematically classify 4 factors that go into the design space of AR labels. Here, I will give you some examples under each dimension. For the entire design space, please see our full paper. So first, we consider how the objects are represented with the label proxy. Designers can decide whether labels are shown for in-view objects, out-of-view objects, or both. Second, proximity is an important factor to be considered for the label placement. Labels can be placed close to the object to support faster linking or close to other labels to allow easier label comparison. Third, label placement can encode different object attributes to provide extra information, such as encoding the vertical position or the direction, or rank the labels by the value to allow value comparison. Finally, to support spatial search, we also consider how AR labels update in response to the user interaction. Designers can consider the label movement pattern on the AR screen, or whether the labels react to the user's body or gaze movement. So based on this design space exploration, we propose 5 distinct labels. The first 2 labels only encode the in-view objects. Situated is a baseline condition, boundary is an alternative design to avoid visual clutter. I will show the videos in a second. 3 other conditions encode the out-of-view objects with different object properties, including the vertical height, the angle, and the value property. To implement the labels in our study, we use VR to simulate the object space and create an AR screen on top of the view. The user is surrounded by the objects represented as a cube. Each label has a unique name and a randomly assigned rating. I will show the videos next. So here's a screenshot of the VR view. You can see there's an overlay AR screen, and labels are only visible on that AR screen. So in the video, user is rotating while standing still, so you will see the objects coming in and out of the view, and labels are updated accordingly. So the first label, situated, they are placed close to and above the virtual objects. Boundary labels, they are placed at the bottom boundary of the AR screen, and they are linked to the object with a leader line. Height label encode the relative vertical position of the objects that are outside the field of view. And once the objects are in view, labels become situated. And labels are placed on the left or right boundary depending on which way the object is closer. And angle labels encode the object's relative direction to the user from the top-down view. So the top is the front and bottom is the back. For example, the object with the green label on the bottom left of the AR screen is behind the user to the left. So the labels will rotate around the AR screen as the user turns. So finally, value labels rank the labels by the values, and they are placed at a fixed position on the left boundary of the AR screen. A left-right arrow indicates the closer direction of the object that's outside the field of view. To evaluate which encoding technique is most useful for the situative visual analytic task, we conduct a within-subject user study with 15 participants. The user was asked to identify an object, compare 3 objects' values, and summarize the value average of 2 clusters. We record the time, accuracy, and subjective feedback. I will share 3 main results. First, we found that users perform compared tasks significantly faster with the out-of-view object labels. It is mainly because users can compare multiple objects at once and do not need to scan the entire surrounding area. Second, situated and boundary labels have similar performance across all tasks. Third, angle labels had the best performance overall in supporting situated visual searching tasks and was preferred by the participants. To conclude, our study results provide design implication for future AR applications. On the high level, in-view objects labels can be suitable for targets that are within the same direction, such as a few products on the shelf. Or for tasks that involve sparse objects in the physical environment, out-of-view labels can be beneficial, such as an entire fruit section in a supermarket. Alternatively, boundary labels can be applied when less visual clutter in the center of field of view is desired. For out-of-view objects, angle labels are good for searching the target location, like coffee shop in the area. Height labels can be used for targets with various height, like books on different shelves. And finally, value labels with static layout can be used to track the ranking of targets effectively, such as the athlete's ranking in a race. So with that, I'd like to thank you and also thank my wonderful collaborators, Yalong, Johanna, and Hans-Peter. I'm happy to take any questions.
Fantastic. Thank you for an interesting talk. So, like we talked about in one of the earlier talks, sometimes it's really hard to do the mental translation between what we see on the 2D screen when we're presenting these results and what we would otherwise see in the headset. So I'm curious if you can talk about a little bit more about how you might translate these labels and this kind of work to more of a perceptive, immersive environment like we have in the HoloLens, rather than a flat screen like an iPad or what we're seeing on the display here.
So I think in our study, we actually use the head-mount display. So it's more similar to the AR glass scenario I would mention. But yeah, one interesting thing is the angle labels by design it requires more context switching. So you need to kind of like a radar projection of your surrounding area onto this AR screen. We expected the user will need more time to learn it and might be difficult to perform the task. But actually in the study, after some training, the user can naturally project this information and find the location of the surrounding objects pretty naturally. Yeah.
Fantastic, thank you. And we have another question on Slido from Jorge Wagner. Great work. I understand that you used a VR headset, but simulated the field of view of the HoloLens. What are your thoughts on the effects of a larger field of view and what those could have on, what effects those could have on your findings?
Mm-hmm. Yeah, so we choose this virtual AR screen size according to like what's the available AR field of view of the current technologies. So I think one thing we consider is even if the field of view can be larger, if you put the labels or like other indicators on the screen that's on the peripherals, it might not be helpful for the user to like compare and analyze while they're looking in the front. So actually during the study, we asked the user if they can effectively compare all the labels on the screen, and the answer was yes. So yeah.
Great, thank you so much. Let's thank Tika again and thank all the speakers from this session. That wraps our session for today. There are coffee and snacks out in the hallway, and the in-person speakers will be up here afterwards for any additional discussion. Thank you all so much.